Hi, I'm Atul and I am in London right now.
Hi, I'm Paul and I'm in Burnley, Lancashire right now. So today we're going to have a look at Hess's law calculations. And Hess's law is the enthalpy change for a reaction is independent of the route taken. So we'll have a look at a question that we can use Hess's law with. So we've got calculate the overall enthalpy change for this reaction, and we're given enthalpy of formation data for the compounds in this reaction. So make that a little bit bigger. And because we're given enthalpy of formation data, then that's the enthalpy change for forming those compounds from their elements under standard states, under standard conditions. So we can put arrows towards the compounds that we're forming. So we can just write we're forming those compounds from their elements. Or if we want to balance it chemically, we can write down those elements would be carbon, hydrogen, and oxygen. And we'd need 2 H2s and 2 O2s to balance. But we don't need that for the calculation. So, and then we can just write the enthalpy changes on our arrows. So for methane, we have minus 75. For carbon dioxide, minus 393. And for H2O, that's minus 286. If you notice, these enthalpy changes are per mole, and we're forming 2 moles of H2O, so we need to times that by 2. And then if we call the enthalpy change for this reaction X, we can now use Hess's law to calculate the enthalpy change of this reaction. Now, there's 3 ways of doing this. So the first way, if we look at the arrow, now the enthalpy change for this reaction is going from reactants to products, which is going that way. And going that way, we're going against the arrow for the reactants, but with the arrows for the products. So we can say X is equal, because we're going against the arrow for the reactants, we change the sign of that reaction. So the opposite reaction would have the opposite sign. So that would be plus 75. And then the other 2 arrows were going with those arrows, so that enthalpy change stays the same. So all we then do is put that into our calculator. So 75 minus 393, add minus 286 times 2, and that's minus 890 kilojoules per mole. And then the other way of doing this is to look at the arrows and see that some of the arrows are going clockwise and some of the arrows are going anti-clockwise. So the minus 75 and the X are going clockwise in the normal clock direction, and the minus 393 and the minus 286 times 2 arrows are going in the anti-clockwise direction. So because this is energetically equivalent, we can say the clockwise arrows equal the anti-clockwise arrows. And we would therefore say that minus 75 add x, so they're the clockwise arrows, is equal to minus 393 add minus 286 times 2. And they're the anti-clockwise arrows. And if we rearrange all that, we get x equals minus 393 add minus 286 times 2. And moving the minus 75 to the other side of the equation would give us plus 75. And we see we've got the same equation we started doing the other method, and that would equal minus 890 kilojoules per mole. So slightly different method, but same answer. And the last method we can use, and I don't like this method because we've got to remember an equation. And I can never remember the equation, and students often get the equation wrong and the wrong way round. And I can only actually remember the equations once I've done the cycle. And so we can see that if we're given enthalpy of formation data, then our enthalpy change is equal to the enthalpy of the products, or the enthalpy change minus the enthalpy change for reactants. And if we're given combustion data, that's the opposite way around, and how we're supposed to remember which one's which. So the enthalpy change, so if we look at the enthalpy change for the products, which would be minus 393 add minus 286 times 2. And then we subtract the enthalpy change for our reactants, which is minus 75. Then that would change the minus 75 to a plus, and we've got the same equation, and our enthalpy change again would be minus 890 kilojoules per mole. So 3 different methods for calculating enthalpy changes using Hess's law, and I would prefer either of the first 2 methods because there's no equation to remember and get wrong. And I would recommend using the first 2 methods for this sort of question.
Yeah, that's pretty neat. Yeah, yeah, like the second one is more like I suppose like a moments, anti-clockwise moments and clockwise moments are the same sort of in physics, but just with energies, isn't it? So all the energies on the left.
Yeah, it's like a conservation of energy.
Yeah. And the enthalpy of formation of oxygen must be 0, obviously, because that's an element. So that all you're left with is X methane.
Yeah.
And then on the right hand side,
And you could show that. You can actually draw that arrow in for oxygen, but just put 0 there. And that's often a question in, why is oxygen enthalpy change 0?
Right. Yeah, presumably the enthalpy of formation is defined as the enthalpy of formation from the element. So if the element is the element.
And you can see there we're just going from the element to the element, so there wouldn't be an enthalpy change. We're just going, because we've drawn the elements in there, we can see we're just going from 2 oxygens to 2 oxygens, so there's no enthalpy change.
Yeah. Yeah. Great. Sounds good. Very neat. Gives our students a few options depending on what sort of procedure they prefer. Yeah. Brilliant. Looking forward to the next one in energetics and Hess's law in general.
Yeah, okay.
Bye for now.